Hi, this is Saivurapalli. Today I'll be presenting you my understanding of solution for the assignment 10 here. So in assignment 10, we are implementing the deep learning, deep Q networks where we implement a model, we implement a train model to select the action, and based upon those actions, we're going to implement the reinforcement learning. So in this assignment, the environment that we picked was balancing a cart pole. So our main, so as we could see here, there is a object, and then the cart pole is so a cart pole is connected to it. So a pole is connected to the cart. So our goal is to make sure the pole stays, straight. I mean, it doesn't fall. So we're going to start by implementing, importing all the necessary libraries that we're going to need. So once we implemented the necessary libraries and the environment that we're going to work at, so we're going to just look at the environment. So in this environment, we have two actions, 0 and 1, whether to push the cart left or whether to push the cart right. So our observations, so those will be our actions. And then our observations are, what's the position of the cart and what's the velocity of the cart and what's the angle of the pole and the velocity at the pole tip. So these will be our feedback or the observation. And then our reward is for every action taken. So for every action taken, if the pole stays same, I mean, like if the pole doesn't fall, then you get a positive reward, positive 1 in this case. So our main goal is to get the maximum reward as possible. So by generating the actions from the classifier or like from the model. Okay, so in this, we're just going to look at the environment, just generate some random action and then see like how the environment is behaving. So here we selected the action 0, which is push the card left. And once the cart is pushed left, and these are our observations. And then our reward is 1. So that means the pole was straight. I mean, like it didn't make the pole fall. And then is false. And then the info is what our limitations. So this gives our limitations. So one would be the limitations for our observations. So what our observations are like for cart position, cart velocity, pole angle, and the pole velocity. So those are the limitations for the observations. And then now we're gonna define the action function here. So in this case, what we're gonna do is we're gonna implement, we're gonna start by implementing a generating a random number. If our random number is less than the exploration rate, then we're gonna select a random action by using the random dot choice. But if our random number generator is greater than the exploration rate, then we're gonna use the DQN agent model that we're gonna implement. It's shown in the further steps. So we're gonna predict based upon the observation. We're gonna predict the action from the model that we're gonna implement, and then we're gonna see, okay, what's the maximum. Okay, we're gonna predict from the observation. We're gonna predict the maximum value for both the actions. So and see which action has the maximum Q value, and then based upon that, we're gonna take the action. So that's how we select the action. So this is the action function that we're gonna define, and this is the Q value. This is the algorithm that we're gonna implement, and in the code to train the model on the memory of the experiences collected so far. So based upon the previous memories, I wanna train the model more and more. So based on for that, we are just initializing the state badges, Q value badges, and then okay for whatever the current observation and the action and the reward, and then the observation next. We are gonna implement our target function, which is the reward function plus gamma of the maximum action of the next observation. So here, this is our reward plus gamma into NP A max of the target action dot predict. So this is this target action is the DQN agent. I mean, like the model that we train. So based upon the observation and the further observations, it's going to generate Q values for the actions. And then np.amax will select the action which has the best, or like which has the highest or the best Q value. So that would be our target, else our target will be target. And then based upon the so our Q value would be based upon the current observation, whatever the value we get, that will be the Q value. Since we had two actions here, we're going to get two Q values, and then we're going to update the Q table with the action taken. So based upon the np.amax, we're going to get the maximum, we're going to select the action to be taken, and based upon the action taken, we are going to update our Q value. So once we do that, we're going to append all the observations, so like all the Q values that we had, and then we're going to refit our model with the updated Q values. So every time, every time the model learns something new, or every time when the new Q values are generated, we are going to train our model again. And then our train model is going to generate a random action, and then we're going to take the action again, generate the Q values, and again, it's like a repetitive process. So your classify, like your model will give an action. Based upon the action taken, it's gonna update itself, and then again give you new actions. So in this case, we are setting our maximum episodes at 75, and our gamma as 0.95, and memory and target update steps as 10. And then number of actions will be the total actions that can be taken place. So in this case, it's 2. And then the number of observations will be 4 in this case, because we got cart position, cart velocity, pole angle, and then pole velocity at the tip. And then we specified our batch size and the learning rate and our optimizer as Adam. And once we set our parameters, then we're gonna start implementing our model, sequential model here. So here we specified as DQ and agent, initialized our model, and then added the dense layers with 64 units and 24 units. And then activation functions as ReLU. And then at the end, we want all this converts to the number of actions we're gonna need. So in this case, 2, and then the activation function as linear. So here our number of action is 2, so that's why our output has 2 dimension. And then we are going to compile the saying by implementing the loss function as mean squared error, and then the optimizer as Adam, and then we are implementing the learning rate for Adam as a learning rate, which we specified earlier as 0.0001 or 1 e power minus 4. So once we got our model, we're gonna again set our epsilon value. Okay, start at 100% or 1, and then decay rate as 0.95, and then stop at 0.05 and maintain that. Our minimum epsilon value is 0.05. So once we define that, we're gonna start our function here. So we initialize the function. We're gonna implement the start timer to see how long it took for the model to train. And then our maximum episodes in this case was 75. And then we're gonna reset the observation. And then once done, we're gonna implement the select action function that we had earlier. So based upon the current exploration rate and the current observation, and then the DQ and agent, we are gonna get an action from this select action function that was defined. So once we got the action, so for the action taken, what was our observation next, and then what was the reward, and then what was whether it was done, or and then the info. This will be our what do you say, this will be our observation in this case. I mean, this can be drawn from the environment once we take an action. So now we're gonna gather our experience. So once the action is taken, what happened? So that we're gonna feed it, and then we're gonna look back into our experience. We're gonna use that memory to perform better in the future action. Perform better. So in this case, our experience would be the current observation, So what's the model is, and then the action, and then the reward. So once taken the action, what the reward I got, and then based upon the action, what was the observation next time, like what's the state of the environment, and then whether it is done. So this is our experience, and then we're gonna gather all our experiences by using the append function here. So once we gathered all the experiences, our next task is to, sum up all the rewards that we got for each for the episodes, and then also, increment the time step. So now we're gonna print everything, look at how the model is running. As we could see here, for each episode, the exploration started to go down, and then this was the maximum score that we got here. We got like 27 points, or 27 value of 27. So that means for that episode, the agent was able to make 27 actions without making the pole fall. So again, our goal is to get the maximum reward as possible. So once we train the model, so once we train it based upon the memory, it always tries to perform best. And then we're gonna plot at the rewards collected over for the 75 episodes. And then once we plot the reward, we're gonna look at how our model, or like how our reinforcement learning agent has performed on the environment. As we could see here, it tried to balance the pole for a certain instance. So in this case, our episode was like for 75. So if we train our model more, it's going to update the Q values, and then based upon the Q values, the classifier, or like the neural network, will give you the best actions and try to generate the maximum reward as possible. So we're going to load a pre-trained model here and see how it was done. So as we could see here, our agent is trying to balance the cart pole. So in this case, our reward was maximum. So this is how we implement the deep Q learning, where you implement a neural network to generate a random action, and then based upon the action, you generate the Q value. You take the action and get the Q values, and then using the Q values, you're gonna update the neural network model again, and then the model generates the better action and next time. So this is how your reinforcement learning agent will learn more and perform better. Thank you.